like Tim Madsen did, I've provided an online GitHub repository for all the code material for the class. Sometimes I feel, and maybe I have a show of hands, you don't learn coding unless your hands are hitting keyboard, right? There's that process of the information going through your eyeballs to your hands. Some of it gets stuck in the middle. So I really want to encourage you to hit keys with hands just to actually get that sense of you're programming a GPU. And that's the goal today, is to give you some very basic introductory material, not highfalutin, not high level, straightforward programming of GPUs, initially with CUDA. Okay? So we'll basically go from scratch, hello world, CUDA style. Okay? Does that sound good? Right. Okay. So that's the repo that you can use. We're about to send some little cheat sheets. We'll send a physical cheat sheet round to you. Hopefully there's enough for everybody. I feel like I need to give a counterpoint to some of Tim Madsen's comments, of which there were many. Tim, I know you'll be watching this. I feel like I really need to call you on some things. In particular, playing the victim as a employee of a company with a market capitalization of $220 billion. Right, so the first thing is I really like, so I've actually followed Tim's presentation for the last 4 years. I always have to sit there because I come early and then I see his presentation. And I can say one thing, OpenMP doesn't seem to be getting easier. And that's in part because Intel's CPU infrastructure is getting more complicated. But we'll come back to that in a moment. But the good news is, as somebody who's contributed to OpenCL, he is now admitting that it is important for you as people engaging in supercomputing to pick up some OpenCL or CUDA. And I'm pretty much directly quoting what he said. Okay, that's a bit of a sea change since in the last 4 years. Previously, the message was, OpenMP will take care of it. OpenMP 4.4 will take care of it. OpenMP 4.5 will take care of it. Oh my God, it's a hell of a mess to program GPUs with OpenMP. Okay? That's essentially the trajectory of what we've heard from Tim. But during his rant, sorry Tim, during his rant about the Nvidia PR department, and I hope you picked up on this, he's accidentally telling us something about Intel hardware. So he's correct. In the early days of GPU computing, some papers came out with outlandish speed-up reports. 100 times. I've even seen 1,000 times speed-up. Okay? But what do you think that actually says about the CPU? Not the GPU, about the CPU. Anybody like to hazard a guess? The CPU is actually pretty hard to code at to get good performance. That's the thing that he's omitting in that rant. The problem is, and it's actually built into Intel's their business model, is when Intel was a single, or Intel AMD had a single architecture in the market, it was not in their interest to have users completely optimize their codes, because they wanted users to be incentivized to upgrade every year and a half. That's what Moore's law is. It's not that CPUs get faster every year and a half. It's that you should upgrade every year and a half. Okay? So if your code doesn't run so fast, you are highly incentivized to upgrade your CPU. Unfortunately, that model fell apart in the mid-2000s, about 2005, when they couldn't keep increasing the clock speed. So if you bought a CPU in 2006 and a half, it ran at the same speed as the CPU you bought in 2005, if you didn't do anything with your code. And then there's a huge amount of complexity that's involved in Intel trying to keep increasing the speed of your code every time you upgrade your CPU. So we see that complexity expressed in OpenMP, where they're trying to retrofit parallel computing into Intel CPU environment, into its ecosystem. That means the compilers, the debuggers, everything else, the architecture. And if we're talking about PR, I would say that NVIDIA, okay, what NVIDIA was highlighting was not that their hardware is super sophisticated and super fast, but that you could actually get speed-ups by doing what NVIDIA told you to do. They told you we can't just program the GPU like it's a regular CPU. They said you have to pay attention to these things. And there was literally a list of things you needed to pay attention to when coding at a GPU. Memory access, data locality, and threading. You have to pay attention to all of those things to get good performance in the original GPUs. Intel said, oh, just recompile with the latest compiler, you'll run, and it'll be faster with the new CPU. NVIDIA said, no, hold on a second, that's not a sustainable model. Now, the apex of that marketing promise was that Intel promised that you would get GPU-like performance out of, and then a sequence of products that may or may not, or did not appear in the marketplace. Okay? As domain scientists, engineers, physicists, geophysicists, whatever your domain is, you don't want to rewrite your code, right? So as long as there's a promise that there's new architecture coming that will be faster than the current architecture, or new processor that's faster than the current processor, if you don't have to write your code, rewrite your code, you'll just wait. And that's been Intel's position in the marketplace for about several years now, almost 10 years, okay? So, unfortunately for Intel, Nvidia is eating its lunch in terms of delivering performance in data center applications. So if you look at machine learning, if you look at the latest high-performance computers, the big systems like Summit, most of the flops are delivered not by Intel's solution, but by NVIDIA's solution. Okay? Does this make sense? Okay. So, what's worse? NVIDIA saying, okay, essentially Intel's CPU is hard to get performance out of, or Intel saying, trust us, wait, we'll give you a solution, and then not delivering that solution for performance. You tell me. What's interesting is actually, if you can look on the internet, you can actually look at the market capitalization of Intel and the market capitalization of NVIDIA. Market capitalization for NVIDIA is following that top curve. Market capitalization for Intel is sort of following this curve here. It's almost like you can put these curves on top of each other, because NVIDIA is doing smart things with their hardware and delivering high performance. Intel is doing very, very smart things, but we're struggling as developers to get performance out of their systems. Okay, that's my rant over. So I'll give you a quick overview. First of all, I'll talk about some of my research, why I'm here, why the Argonne guys keep inviting me over year on year. And then I'll talk about some actual GPU myths, give you some idea about GPU architecture. I'll talk about the CUDA programming model. And then I don't think we'll talk about optimization, but we'll talk about alternatives to programming with CUDA. And then the fun part at the end is we'll have a competition to see who can use a CUDA or CUDA accelerated flow solver to generate the coolest looking animations. Okay, so there will actually be prizes. So the idea, and you want to, when you get bored with me talking, which I can see some of you already there, you should track down a PNG image file, preferably not very, very large one, because the compute time is proportional to the size of the image. So find a cool image with a white background, and we can do flow over that image, okay? So you can use this sort of pre-canned lattice-Boltzmann solver that's in that repo, and you can generate some cool flows over objects. So what we do is we try and detect background where the image is white, and we'll treat that as the flow domain. Where the pixels aren't white, we'll treat that as, it doesn't have to be perfectly white, we'll treat that as the wall domain, okay? There are cash prizes. I can see you suddenly paying attention. There might be money available in the form of Amazon gift vouchers. And so the top prize will be a $50 voucher, 2 second prizes are $25, and then there are some fairly pathetic swag for the next 4 best movies. Okay, right? So get that brain thinking. You can be really quite creative here. I kind of messed up the selection. So you really want to get something that's white, choose the right thing. But I had a stick man that I drew by hand, took a picture of my camera, and then you can use that as a flow domain. Okay. So exercise your creativity, and we'll have a vote after the session. Marta will send around an email where you can vote on a Google form, and the winners get the cash. Okay. Just to make it a little bit more fun than it might otherwise be. So what is my research? Why am I here? Well, I'm a mathematician. I think we've heard from Phil Colella, who says he's a mathematician, and Tim, who says he's a chemist, right? Notice we're not computer scientists. And I think that's quite important talking to you all, because a lot of you are actually domain scientists. So you're getting a domain scientist perspective. But I'm actively involved in every part of the simulation toolchain. My research group works from approximation theory, proving things about numerical methods, up to simulations, acceleration, and scalability. So we go from soup to nuts on the whole toolchain for, in this case, numerical flow simulation, but we've done a whole number of different applications. So if I look at this one in particular, we worked with some actually MD PhDs at the MD Anderson Cancer Center, where they had a very time-sensitive application. This is a surgery planning tool. The idea is that if you have an inoperable tumor, or a tumor that would be hard to excise through conventional surgery, there's this new therapy where you can take a catheter, drill a hole in the patient's skull, inject the catheter into the patient's brain. It's a fiber optic catheter, so you can light it up with a laser. And you can basically, kind of like an easy bake oven, you can use the light from the energy from the laser beam to ablate the tumor, to kill the tumor. Just had to cook it to a certain temperature. Now, this presents a lot of planning issues. Where do you drill a hole? Where do you put the catheter? What power do you put on the laser? How long do you run the therapy for? And how many times do you run the therapy, right? And the goal is to optimize the therapy before you start working on the patient so that you can optimize the dose delivery, right? Now, the patient's in the MRI. We can get MRI data live. So we wanted to create a control loop. But if you use an off-the-shelf finite element code that isn't accelerated, it would take several hours on a cluster. That's not really compatible with a surgical procedure, especially if you're in a queue, if you're queuing up your job on the cluster. So the application constraints basically said, well, we have to run this live in real time in a workstation that can fit in the booth next to the MRI machine. Okay, so we have seconds to do these calculations. And this was a few years ago, so the only thing that would deliver that kind of performance was a GPU, but we didn't happen to have a finite element solver that could solve that problem that fast, so we actually wrote one that could could model one of these therapies in about 17 seconds. So we could actually integrate it into the therapy planning and potentially put it into a live optimization loop to, on the fly, decide how to treat the patients. Other time-sensitive applications. So some years ago, we were looking at tsunami modeling. One of my graduate students was from India. He's rather affected by the Indian Ocean tsunami, so he wanted to be able to deliver workstation scale solutions to regional governments in India so they could actually do some tsunami inundation warning type things. So there's a lot of different applications. Currently, we're part of a DOE exascale center where we're trying to help upgrade DOE finite element solvers to work on exascale. So this is a huge project, and we're one part of it. And what we've done is we've taken some existing finite element codes. So this is an example, it's the NEC 5000 code. We've basically created a whole new engine that does incompressible flow simulations, compressible flow simulations, gas dynamic flow simulations with bang up-to-date technology in terms of approximation, in terms of discretization, but also in terms of parallelism. So we have developed a new engine for this solver, and it can be deployed on either Nvidia's GPUs, AMD's GPUs, Intel CPUs, or pretty much anything you can run OpenCL on. Although we did not get to the FPGA yet. That seems like another bridge to cross another time. Okay. And it's open source and publicly available. In fact, if you click on this, if you go to the GitHub page, you can see there's some links, and you can click on these slides, and then you can click on some of the resources that go with it. So that's my team, right? That's what we do. We live GPUs day in, day out for the last decade, right? We have an immense amount of experience working with these devices. Okay, so that's some of the material for today. Let's do the quick reality check. Myth number one, despite the papers, GPUs are not intrinsically 100 times faster than a CPU. An ideal implementation of a problem on a GPU will not run 100 times faster than an ideal implementation of a problem on a CPU. There are no circumstances under which that is the case. In particular, if you look at the main performance limiter, this was from last year. The Nvidia P100 had a bandwidth of 700 gigabytes per second. A single socket Intel CPU had a bandwidth, so that's a communication between the device or the CPU and the memory, was about 80 gigabytes per second. So if you are memory limited, you get to see about a factor of 9 times speed up. If you've got 2 of those CPUs, you see about a factor of 4 times speed up. That's the realistic expectation. It seems like a lot of work to have to recode for this so you can get 4 times a dual socket Intel CPU solution. Okay? Having said that, it may be easier to get peak performance out of the GPU than the CPU, as I've alluded to. This year, if you buy the top-end GPU, it delivers 900 gigabytes per second by using some HBM2, some second-generation high-bandwidth memory, and compare it to the current top-end CPU, which is 120 gigabytes per socket. So again, it's about 3 times, 4 times faster in terms of raw amount of data that can be moved around per second. Okay? That's assuming your problem doesn't sit in L1 or L2 cache. Okay? GPUs are expensive. I would wholeheartedly agree with that. Now that there are 2 main players, one Intel in CPUs, one Nvidia in GPUs, plus AMD sort of at the heels in both of those markets, both of these large companies exercise market position, authority, and pricing. So the top-end GPU last year was about $5,000-$6,000. Top-end CPU was $9,000 per socket, I think. Wow, okay. This year, well, the prices went up, $7,000 to $12,000 each per current generation GPU, or $10,000 per socket for the highest-end Intel CPU, right? So by my advanced high school math, this is approximately the same as this, right? I wouldn't say GPUs are expensive. However, you can buy something which is very close to this, but is a consumer variant or prosumer variant, which is a Titan V GPU, which is $3,000. The only difference is the amount of memory and some amount of memory stacks and the amount of memory that's available on the GPU. And this is, of course, the most exaggerated CPU price I could find. This is their super, super duper platinum model. You can get the same bandwidth for a lower cost CPU piece. Myth 3, CPUs and GPUs are very different. Well, here's a couple of examples. Here's the Pascal Nvidia P100. Whatever Nvidia says, it doesn't have thousands of cores, it has 56 cores. Each has 4 32-way SIMT units. The Intel of comparable generation had 24 cores with 256-bit AVX2 instructions. So marketing speak aside, they're just multi-core processors, and each core has vector processing units, or units, okay? Just ignore most of the fluff and sort of marketing speak. They are actually convergent in the sense of architectures getting similar over time, not more different. Myth number 4, OpenACC is magic. If you just liberally take your code, C, Fortran, whatever, and you liberally decorate it with some OpenMP-like comments, or you can actually substitute OpenMP 4.5 here, the same comments apply. If you take a regular code and decorate it with directives, you are very unlikely to get best performance out of a GPU. The only instance where I've seen high performance out of an OpenACC code is when somebody's taken a CUDA code and converted the CUDA API calls to OpenACC directives. Because the way we program in CUDA forces us to pay attention to data locality and efficient threading. So it is possible to get performance out of an OpenACC code, but just dumping a bunch of directives into your code is probably not going to deliver any decent performance. And I'm going to be super cynical here, even more cynical. Nvidia is pushing OpenACC as a programming solution for Nvidia GPUs. I will refer you to my previous comments about Intel. It's not necessarily in Intel's interest for you to write the fastest possible code because you lose incentive to upgrade your CPU. Now Nvidia is in that market-leading position, so it's no longer in Nvidia's interest that you have the best possibly tuned GPU code. So they're quite happy for you to use OpenACC, deliver subpar performance because your incentive to upgrade to the next generation GPU is increased. Okay? So that's my viewpoint on that. Other people have different viewpoints. Having said that, CUDA programming of GPUs is also not a magic bullet. You do have to pay attention to how you program these GPUs to get best performance. We'll see why in a bit. So it takes more than 3 hours to master GPUs. We can discuss some of the basics. I'm setting you up in some ways so that the Raja and Cocos talks make a bit more sense. And they may be easier ways to program GPUs than writing everything from scratch in CUDA. There are lots of web resources, but nothing beats hands-on. Okay. So I'm going to shortcut my description of the history of GPU computing, where we switched from, well, where the transition points from CPU architectures to GPU architectures. A modern CPU style, if you abstract it and look at it from 10,000 feet, is quite, it's divided into these logical units. You basically have, for every core, you have an instruction fetch decode unit, an arithmetic logic execution unit, and you have out-of-order control logic, branch prediction logic, memory fetch, prefetch units, and large caches. In the original GPU design, most of this was thrown away. Okay? NVIDIA's genius move was to take out the layers of middle management that make it so that your single-threaded CPU code runs efficiently. They got rid of the management layers. They put the onus on the programmer to get performance by exposing raw cache hierarchies. So they forced the programmer to pay attention to when data was fetched, when it was cached, and the set of instructions, the sequence of instructions. The GPU application is actually very straightforward. It involves a lot of geometry. So this is an old picture of a rendered human-ish face. And the GPU is responsible for each pixel, each little block that makes up this image. They have to decide the red, green, blue, and alpha components of the pixel, basically the coloring of the pixel. But you can compute the pixel over here independently of the pixel over here. So if you dedicate a thread to compute the pixel here, and just imagine there's a set of polygons that represent this head, that involves basically marching a line through a set of polygons, finding intersections, and then inspecting the image or textures associated with each of the polygons on this head. You can do this pixel, you can have a thread compute the intensities for this pixel independently of a thread that's down here in the grubby cheek area, okay? So if you had 1,000 by 1,000 pixels, you have 1 million independent tasks, okay? So a GPU is originally designed to manage that type of massively parallel operation. In fact, it's embarrassingly parallel operations because these pixels can be computed independently. I just zoomed in on one part of it. And it has to be done quickly in the sense of if you want to be a AAA gaming title, and that's the money that's supporting the whole general purpose GPU computing environment, you have to be able to deliver 60 to 90 frames per second at 4K resolution. So that's, let's say, 8 million pixels, 60 times a second. So that's 500 million operations that have to be performed. And each of those operations consists of a chain of operations to determine the colors of those pixels. So what's a little bit different between a CPU and a GPU thread is as long as the frame is computed in 1/60th of a second, it does not matter in what order those pixels are computed. So if I'm computing a pixel over here, and for whatever reason the thread stalls because of a memory request or whatever, it doesn't matter, as long as it stalls for less than 1/60th of the second, okay? So it's kind of a different application, but it's quite a targeted application. And we were able to, so in some sense, hijack the hardware. So just to summarize, on GPU, throughput matters, single threads do not. So you can think of this as communism or socialism, right? The single person doesn't matter, it's the collective that matters. Whereas Intel is completely the other end of the spectrum, right, where you have the thread matters, the single thread is supreme, right? It's capitalism. Everything about, it's most important to keep that thread busy, right? But you can see why there's a clash of cultures between Nvidia and Intel. You've basically got capitalists versus communist or socialist. The GPUs still have the same type of high latency memory problems that the GPU has the same kind of memory latency problems the CPU has. And by exposing the raw cache hierarchy directly to the programmer, it puts the onus on the programmer to be smart on how to fetch data, when to fetch it, where to put it. Did you put it in Reg? Did you put it in shared memory? What did you do? Okay. And they resisted the siren call of Intel's business model. Intel's business model until the mid-2000s was just increase the clock speed. Unfortunately, when you increase the clock speed, the energy dissipation of the chip increases in sort of the cubic, in the cube of the frequency. So they actually have a larger budget for energy budget for compute than, say, an Intel processor has. Okay, so here's an early AMD die shot. It's basically a colorized image of the processor die. And you can see most of the architecture, most of the silicon is spent in the single instruction multiple data cores, the vector units. That's all of that is compute. This text unit is a fancy cache that can also do arithmetic. You fetch data from the texture cache, and it will do linear interpolation on the fly for you in hardware. Okay? So all of this part of the chip is dedicated to work, floating point unit work. If you compare it to a contemporary CPU, everything on the Intel, or this was something else, everything on this chip, except for this part here, was dedicated to management. Okay? So as some of your graduate students or postdocs, you'll appreciate this analogy. This is a university. You have the faculty who don't do much work, right? Because they offload work to you all. That's the graduate student. Okay? My ideal university, no administration, very few faculty, and an immense number of graduate students, right? So this is the graduate student university, which is the GPU, and here we have the poor oversubscribed graduate student, the administration, the faculty, and everybody pointing at this poor student to do all the work. Okay, so let's look at a specific GPU architecture. This is a little bit old. It's an Nvidia Maxwell. This is one core. Notice that Nvidia calls each of the compute lanes inside the SIMD unit, the vector unit, it calls that a core. That's why Nvidia says that its processors have 2,000, 3,000, 5,000 cores. What they're actually saying is they have 2, 3, 5,000 execution units, or individual vector units, or lanes in vector units, okay? But if you look at this carefully, it's a 16-core processor with, in each core, they have 4 vector units, okay? You'll also notice, but you can't read it, it has some cache. So each core has its own shared cache and its own L1 cache. Nowadays, the shared and L1 cache are unified, shared. So I'm stressing the similarities between CPUs and GPUs. They're multi-core devices with vector units in each core. Okay? Why don't we just program like we program an Intel CPU? Well, there are some fundamental differences. Each CPU core executes scalar or vector operations using scalar registers or vector registers for historical reasons, because vector registers were added later than scalar registers, right? So originally you would add 2 variables. Then, because they had more real estate on the silicon, they added vector units so you could add 2 vectors. So the challenge as a programmer is to persuade the compiler that you should be allowed to engage the vector engine on the CPU core. And that's difficult because Intel forces you to make sure that you've signaled to the compiler that the data you're trying to load with a vector load is aligned with a page boundary, that you're allowed to do it, and you really may sometimes have to psychoanalyze the Intel compiler or GNU compiler to figure out how to force it to treat these operations as vector operations. Sometimes you actually have to inject intrinsics into your CPU code to force the operations to be pushed through the vector units. The situation in NVIDIA's case is entirely opposite. Every operation is treated as a vector operation of length 32. Intel's marketing speech calls that a warp of threads. So if you say A equals B, it wants to do that at least 32 times by 32 different threads, even if you just want that thing to be done once. Okay? So there are some fundamental differences. Because of the massive number of floating point units on each of these cores, and because of the limited memory bandwidth, another design decision was made by NVIDIA, which was to make the NVIDIA cores latency tolerant, in the sense of, by adding a large number of register variables, so fast, local memory variables, storage memory variables, it's okay if a task that's dedicated to those SIMD units stalls because data's coming from the GPU memory, it's okay for the thread task to stall because you can context switch and switch to a different set of threads that are ready to process. Okay? So on Intel world, there's maybe a couple of hundred registers per core. In Nvidia world, there's thousands of registers per core. Okay? So a couple of big differences here. Nvidia operations are always vector operations. Nvidia cores are set up so that you can do context switching of threads very quickly. There are some other details, but some of it's just terminology. GPU has multiple cores. Each core has one or more wide SIMD vector units. The SIMD vector units execute one instruction stream. So if I'm going to send an instruction stream to one core, I'm actually sending it to all cores. Each core has a shared memory scratch space, and it has a shared register file, and it can fast switch thread blocks or tasks to hide memory latency. Now, there are some downsides. If you've got a very iffy code, and I use that in both senses of the word, if you think about the code you're working on, is it sort of this nasty, crazy, nested set of if statements? Who's got one of those codes to work with? Anybody honest enough to admit that? Yeah, okay, what's the application? Actually, that can still work. Yes? Somebody else volunteered? Still, depending on what kind of physics, still possible, but you may have to refactor. There we go. So we have this problem because if you want just one thread in a group of 32 threads to do something, you have to basically idle the other 31 threads. Because literally, there is no scalar processing engine on this chip, right? You get 32 threads at a time, regardless of what you want to do. Okay. So that gives you a sense of the architecture. It's a multi-core device. Every operation passed through the cores passes through a vector processing unit, a SIMD unit. Let's talk about some of the evolution of the GPUs. So let's see. This was the Fermi class. It's a little old now. It had, I have to count them now. 1, 2, 3, 4, 5, 6, 16 processors, 32 floating point units per processor. Okay? I'm not expecting you to remember this. It won't be a test, but here we go. This one, the Kepler class, came out about a year and a half later. They're still on roughly the same year and a half period of new product release that Intel's on. 15 cores, but this time it went to 192 floating point units. The Fermi class processor was a processor designed more for general purpose work. Unfortunately, that impacted NVIDIA's competitiveness in the games market. AMD got more market share because this was a great general purpose GPU. It was kind of a meh graphics card. So the pendulum swung the other way, and they went to 15 cores. Each had 192 floating point units, but they didn't increase the shared memory, and it didn't increase the register file, so it wasn't very good for general purpose computing. Okay? So there are some internal tensions inside NVIDIA of games market versus general computing market. Go to the Maxwell processor, the next generation, and it swung back the other way. So now we had 128 floating point units in groups of, that's 16 cores. Okay? So the pendulum sort of swings backwards and forwards as to the amount of floating point performance per core and the amount of the ratio between the register and shared memory space to the number of floating point units. Then we get to the Pascal GPU, and I think of this as the first modern generation GPU because it had strong double precision performance. Those previous GPUs, they were single precision because that's good enough for games. But as the die process shrinks, you get more real estate, you can afford to put more double precision units on the same space. And now we have cores, 60 cores. Each core has, 64 single precision, but it also has 32 double precision floating point units. This is when Nvidia starts to really matter in HPC, because they delivered a performant double precision processor. And it could get to 10 teraflops or something like that in single, and about 5 teraflops in double. Now we'll fast forward to the latest architecture I know of, which is the professional Nvidia Volta GV100. It has 84 cores using 12 nanometer fabrication. So 84 of these, and each core is an absolute monster because there was a die shrink. They went from 28, I think, to 12. And they had more space than they really knew what to do with. And machine learning is an emergent market, and NVIDIA is not one to shy away from emerging markets. So they dedicated extra space in each core to something called a tensor core, which essentially is a half-precision matrix multiplication or something like that. I still haven't figured out how to exploit that part of the chip, because most of the stuff I do it's too critical to be done in half precision, mainly because of the exponent range in the half precision floating point representation. Okay. So single precision is 32-bit, double precision is 64-bit, half precision 16 bits. That means you get, I think, how many bits are in the mantissa for a half precision? Yeah. It's not very many. 5 some bits, because then you need a sign bit, you need an exponent bit, and so on. Bits. So you really don't get much. You get maybe 3 decimal places, maybe, with not a very wide range in the range of numbers you can support. Okay. So all that, to my perspective, is sort of wasted space for application. But it's worse than that, because now, when I want to compute on the latest GPUs, guess who I'm in competition with? The machine learners. And they have an unbounded amount of work, because they have ever-growing databases of data that needs to be processed and modeled, right? So when you get onto the, if you go onto one of the cloud solutions, go up to Amazon AWS or go up to GPU or Paperspace or one of these new systems that have the V100s, you end up getting in queues with the machine learners, okay? So, and I expect it will be the same on the supercomputers. We'll be in competition with the general HPC community, will be in competition with the HPC machine learning community. Used to be the chemical engineers and chemists would be able to take arbitrary number of cycles. Now it's the machine learners we're competing with as well. Now this is a beast of a machine. It has 900 gigabytes per second bandwidth and generates about 8 teraflops double precision, right? This is actually attainable for benchmarks. For our finite element codes, we've not been able to exceed approximately 5.5, 6 teraflops with our high-order finite element codes. At the end of Phil Collella's talk, he was talking about convolutions, optimizing convolution, and so on. And he says, in a parenthetical statement, that, oh, and you could use high-order methods, which means high polynomial degree finite element methods, to increase the arithmetic intensity. That's been our base understanding for the last 20 years. This may be new to the finite difference community, but this is something we've been taking advantage of in the high-order finite element community for 20 years. And this is why we are able to get 50 to 70% of peak performance on these devices. Okay? I think I'll have a rant about that later. So let's just review the trends. Early GPUs had 16 floating point units, single precision, going up to 192. This is the high point per core. Then we start going from 192 back down to 32 with double precisional support, and now we're at the latest architecture. In 10 years, we've gone from 16 floating point units to a buttload of floating point units, plus some extra tensor cores that delivers immense performance on these devices. This roadmap, Nvidia has not been shy about publicizing their plans. For the last 10 years, we've known this trend was coming. This has been signposted clearly by Nvidia. They have performance projection charts. People didn't take it seriously, and here we are now with incredibly performant GPUs. Somehow, the major HPC codes did not pay attention to this for 10 years. These devices are responsible for 80+% performance of Summit and the, what's the other one? Sierra machines. So now you find DOE labs are scrambling to try and upgrade their codes to take advantage of these kind of devices. That's why we're involved in the DOE ECP project. Because, by and large, Intel said, trust us, we'll deliver flops in your energy budget, and you won't have to recode. My group maintains a blog. This is self-promotion time. We maintain a blog. There's lots of things about running on the cloud. We've got these different variations on the roofline models that let us know exactly how well we can expect our codes to perform. We've got lots of advice on optimization, but that's too much detail for today. But you can go, if you're interested, go look at the blogs. Okay. So that's enough dancing around the subject. Let's get to CUDA. Okay, we know the architecture, multi-core with vector processors. I can run through some slides, or should we just write some code? Code? Yay code? Yay code. Okay. Right. So for this exercise, you probably want to be on the Cooley Cooley system. Okay. Is everybody able to get to Cooley? There are some steps that you really want to take on the Cooley system because you have to set up your software environment. So you need to edit your .soft.env. So I'll give you just a few, 5 minutes just to make sure that soft.env file has those extra things so you're ready for CUDA computing. Yes?
So how long have you run the CUDA LDM example? It's running forever.
Is it generating a bunch of images?
I didn't see. I mean, it's running for 40,000 times.
Sure.
Yeah, I looked at it because of the 400,000.
Yeah, it's gonna generate a lot of images. Are we all good? Okay, let's get back to it. Right. So the first step of writing any CUDA is write a serial code first. I'm not kidding you. I mean, my team, we write GPU code straight now, but that's after 10 years. I would strongly recommend a serial code. So what we're going to do is a simple example. As this might need to be bigger, I guess. Can you read that? Okay, so we'll go to serial. I'm going to pretend this is C++, but we're going to write it C style. But just for later convenience, we'll use C++. Right. So any C program. I am a C programmer. I will not apologize for that. We're going to do some printing. We're going to do some dynamic memory allocation. If you're a Fortran programmer, I'm really sorry for you. Right. We're going to need a main program, as everybody always does. So we're going to have some arguments. Okay. I'll tell you what this program is going to do in a second. Hello world GPU style is going to be create 2 vectors, populate them with some values, add them together, write the result out. Okay. So in the serial world, well, let's just use floats, single precision numbers, 32-bit floating point numbers. we're going to need an integer, say how many entries we have. Let's say 100. We're going to do some dynamic memory allocation. Whoops, malloc n times size of float. Okay? So if you're not familiar with allocating arrays on the heap, now it's time that you do know what we're doing. We're just reserving n times 100 times 4 bytes somewhere in system memory. And we're getting back a pointer. And we're going to have 3 arrays. We're going to populate the entries of A with some numbers. We're going to, entry by entry, add those numbers together and put the result in the array C. Let's see. So we'll need a little, I'll need a variable n for the counter. And then for n equals 0, n's less than n, we're going to populate A. And we'll say 1 plus n, populate B, we'll say 1 minus n, so that I know what the answer is if I add these 2 arrays together. All the entries in the array, the result array should be 2, right? If I add entry-wise 1 plus n plus 1 minus n, I'm going to get 2. So I'm going to need a function that adds them together, call it add vectors. Going to need to know how many. Going to need the pointers for the vectors. And because I'm a horrible cut and paste programmer, we'll just make that the function C at n equals A at n plus B at n. So entry-wise addition of vectors. And there's our function. We're going to call add vectors n, a, b, and c. And then we're going to just print out the first 5 entries. And then we'll just return 0. There's something cathartic about crapping out code like this. It's just, you get a nice little flow of just generating code. Okay? Can you see it? You want to go up? Which part? The add vectors? There we go. Oh. It's hard to do this. There we go. What's that about Emacs? Did I hear some blasphemy? Yeah. Okay. I refer you to my previous statement. Okay. And there's the function, and there's the other piece of code, right? Okay. And again, if you can't type quickly, there are some online versions of this. Right. Okay. Simple piece of code, right? We're going to make it rather more complicated when we go to the GPU, but not too bad. Yes, hello.
We actually do have 76 nodes for today.
Yes, good.
What are we printing out? Sorry.
Oh, right, yes. Just let me use the magic of Emacs, and I can show you. There you go. We good? Okay. We just print out the first 5 things, because we don't want to spool 100 entries to the terminal. You know, I could do this. Just cram it up a little bit. So let's just review this. Add vectors, entry-wide addition of 2 arrays. Main function, allocate 3 arrays. Populate the entries in the arrays. Call the add vectors function. Print out 5 values from the array. Nobody called me out on my abysmal memory management. What did I forget to do? Free. 3A, 3B, and 3C. So if we run it, and it does what we hope, right? It just adds those 2 vectors together. The result is 2 in each entry of the array. It's very straightforward. Okay? Does that make sense? Okay, so the next step is, how do I get the GPU involved in this process? What role does the GPU actually have in this process? That's a bit trickier, right? Yes, hello. Sorry?
Yeah.
So she said, take each vector of the components of the vector and do it piecewise. Maybe, I think she's implicitly saying use a thread to do each entry of the...
Take the whole vector, like the second vector and add them together at the same time. Yeah.
That's roughly it. That's conceptually correct. Take a chunk of the vector at a time, send it to a core, send chunks of the vector to a core, let the core do that addition in parallel. This is an embarrassingly parallel operation. And Bob's your uncle. Well, she's missed out some steps. Conceptually, she's right, but there's something we have to pay attention to on the GPU. The GPU is a quasi-autonomous compute device. It has its own attached memory space. So we're going to have to communicate with the GPU, one, to give it the data to work on, two, to give it the instructions it's going to perform, and three, collect the data back from the GPU back to the CPU. Okay? So we're going to have to do some extra stuff. And this stuff is the barrier to entry to using the GPU. It's migrating data to the GPU, forming the instructions the GPU needs, and migrating the data back. Does this make sense? Okay. So that's our serial version. Now let's make our CUDA version. The first thing we're going to do is we're going to change language. We're no longer programming C++. We are now programming in CUDA. So your C++ file should be a CUDA file, a .cu file. Okay? In an ideal world, I would tell the Nvidia compiler to do this. Right? I would say, Nvidia CUDA compiler, please compile my program, make it magically work on the GPU. That would make my life incredibly a lot simpler. In fact, you can compile with the Nvidia CUDA compiler, but nothing we've done in that file engages the GPU at all. Everything that we've just written would be done by this CPU. We have to explicitly migrate the data, explicitly tell the compiler what the GPU is going to do, and explicitly add instructions to move the data back from the GPU to the host. So the first thing I'm going to do, I'm going to ignore my add vectors function for a little bit. I'm going to go to the main function. That malloc is the standard library malloc, memory alloc. It's allocating a space for those arrays on the system heap. That's attached to the CPU. It's not attached to the GPU, not directly. So we are now in an environment where there are two distinct memory spaces. Nvidia would like you to believe there's one memory space because there are 64-bit pointers on modern systems, and there's enough bits that the GPU space and the CPU memory space can be represented by the same pointer because there are bits that are dedicated to the location of the data, right? Some bit says it's CPU, some bit says it's GPU memory space, okay? But that is a logistical nightmare in coding. It's a code maintenance headache. So one convention that people use, you don't have to do this, is we're going to annotate pointer names by h_, which could mean host, or you just put whatever you want there, just to remind yourself that this is a pointer that's legal or is really referencing some place in the heap attached to the CPU, right? But we're going to have to create some shadow memory. So I'll just be clear here. This is host memory allocation. Now, I want to create some essentially duplicate space on my GPU. So I'm going to have to use a CUDA API call, which is the CUDA version of malloc. And that is going to do the memory allocation not on the CPU heap, not on the CPU memory space, but on the GPU memory space. And I'm going to need some pointers. So I'm just going to call them floats C or A. D, C, device, or C for CUDA. Your choice. D, device. Okay? And we're going to call the CUDA memory alloc and say, okay, give me a pointer to somewhere in device memory space that is the start of this many bytes. Okay? This basically says, give CUDA the pointer to this pointer so that it can change the value of that pointer. If you're afraid or confused by pointers to pointers, don't worry about it. Just use this magic incantation. So I'm going to do this for the 3 arrays. Because when I ask the GPU to work on this data, the data has to be resident on the GPU. I'm going to delay this, save this for later. Okay? I've got to do one more step, which is I need to copy the data from the host to the device. So far, I've just allocated space. I haven't populated the entries of those arrays on the device. Fortunately, there's a CUDA API call. It's a little bit long-winded. Okay, so if we read this from right to left, copy data from the host to the device, this many bytes from this place or starting at this place in host memory to this place in device memory. And in fact, I've got one thing I don't need because the device itself is going to populate C by the function call. Yes?
So by that time, the compiler already knows that DA is on the device and not the host?
No. This is how it knows where the data is. This is basically an enum that says, I want to copy from here, which I've said is a host pointer, to here, which I've said is a device pointer. Okay?
Yeah, when have you established that that's a device pointer?
By this CUDA malloc.
Okay, so that automatic CUDA malloc is device only.
No, but for this call, it has created a pointer that's compatible with the GPU device memory. The way I've structured this, there are different ways to use this. Okay? So, just to recap, this says, give me a pointer to somewhere in device memory that can hold a buffer that holds that many bytes. Okay? This actually is a fundamental flaw in CUDA programming. By sharing the address space between the device and the host, it causes immense amounts of confusion. OpenCL uses a different model where they give you buffers, which are OpenCL objects. Okay? Yes, there was a question over there.
Why don't you populate the device?
This is what I've done.
But
why it is necessary to allocate memory first in the machine, in the heap, and then to allocate again in the device, and then to copy.
Because there are two memory spaces. There are two computers involved, the host and the device. They maintain their own memory spaces. If you want to get fast access from a GPU to some memory, then you should use GPU memory. If you want to get fast access from the host to its memory, you should use the CPU memory. So there are two separate allocators, the standard library malloc and the CUDA malloc, okay? Because we are living in a schizophrenic machine. It has its own two memory spaces, okay? Good questions. I'm going to save the add vectors for the last. Now, once we're done, guess what we have to do? I'll annotate that. Copy data from host to device. What do we have to do after we've done the computation on the device? Copy it back, right? Copy result from device to host. So fortunately, we can just use the CUDA mem copy. Again, it reads from right to left, so we're copying from DC to HC, and then we have to change the direction of the copy. Okay? That is part of the understanding of the GPU, that you have two separate, distinct memory spaces, and you have to explicitly allocate space on the device, explicitly copy data to the device, explicitly copy data back from the device. There is a different mode you can use where you allow the system to do this data migration for you, but you may see diminished performance. Okay, and the last thing is I should fix my print statement here so that it's using data from the right place. I should fix up this because we've got HA, HB now. And the bit I really hesitate to go to is how do we shape the instructions for the device? Okay? So this is sufficiently unintuitive that I want to go back to the slides just to explain how you might think about the instructions we need to give to the kernel, so to the GPU, in order to process those instructions to add the entries together. Yes?
Just while we were here, I was wondering, is it the same free command for the...
Ooh, thank you so much. We'll take care of the API stuff first. We'll need to free HA, free HB, free HC, and then CUDA free DA. So you can see there's analogs of the standard library commands in the CUDA API. So the last thing we need to do is add in the CUDA header file so that we've got the CUDA API definitions. Okay. Right. So we've set up the data migration pattern. The next step is we need to figure out how to give the threads that are going to execute on the GPU the instructions they need to perform the task we need to be performed. So I'm going to chicken out a little bit because I could explain it by hand waving. I'm going to explain it by hand waving at slides. So that's the slides here, just recap what we just went through with that one extra bit. But let's just consider this very simple serial function. In this case, we're just setting the values in an array, right? And I've called it serial simple kernel. So this is going to be a kernel we're going to mutate into instructions for the GPU. So it's very simple. And in fact, I forgot to initialize n. So I'm going to range over n to set out values in some array. But this would only work in the serial system. And I have to figure out, I, as the programmer, have to decide how I'm going to, yes, your question? Nope. I have to decide how these tasks are going to be mapped to that architecture, the GPU architecture I described. So what was the GPU architecture? It was multiple cores. Each core has vector units, right? So there's two levels of parallelism. Tasks that are sent to cores and the subtasks that each core processes, okay? And I've got to figure out how to express to CUDA what tasks that get sent to each core and what tasks get sent to each vector unit on those cores, okay? So the first step is there is nothing serial about this GPU. If I just give it a serial instruction, it would just do that on one unit in one vector unit in one core. I would leave the other 5,000 idle. So I've got to figure out how to split this task amongst cores, amongst threads that execute on those cores. Okay? So in this example, let's assume capital N is 20, so my n range is 0 to 19. And the standard mental model that you're encouraged to use in CUDA is loop partitioning or loop blocking. Okay? So instead of thinking of this as a monolithic serial loop over this range, you might think of dividing into groups of 4, and then this set of instructions to set the values of these 4 entries in the array would be sent to one core. These instructions could be sent to a second core, these instructions to a third, and so on. Does that make sense? Because we have to decide what gets sent to each core and then what happens inside each core. So each of those little color blocks is got a number on it. What do you think that number would mean? What's that, sorry? The thing under the curly braces is like the block ID. It's like it's a task that gets sent to a core. It's an index for a set of tasks that get sent to a core. But what about the numbers in the block, inside the little squares? Thread number, right? Has anybody light bulb gone on yet? So can someone tell me in words what this sort of diagram means? Don't be shy.
So there are blocks and there are threads within the blocks.
Yes. Genius, isn't it? It's so straightforward, right? It's a way to partition the tasks, of which there are 20, into blocks, and in each block is a set of subtasks. So if I've thought of this as entry 6 in the vector, then that's going to end up being processed not by the first block of threads, but by the second block of threads. I think that guy there. Right? Okay? So how do we mutate this code into using this type of loop blocking or loop partitioning? So the first way you could do this is thinking about this as a nested, double-nested loop, okay? Where we're going to loop over blocks and we're going to loop over threads. So we loop over 0, 1, 2, 3, 4, 5, and then inside we're going to loop over 0, 1, 2, 3. Okay? So B goes from those macro blocks, and the T loop is the micro block, the little sub block, the micro loop, right? It's still a serial code, but now we've tiled that for loop. Okay? And I'm starting to nudge towards the syntax that CUDA uses. Notice I've introduced the notion of a grid dimension at the top there. Where did I even put? There it is. This is rather close to the CUDA intrinsic variable that tells you how many blocks are on a grid. And this says how many threads there are in a block. Or in our case, this would be how many? 5. And this would be 4. Okay? And they come out of nowhere in CUDA code. They're provided to you as intrinsic variables inside of CUDA function, device function, or kernel. And now, because I've got this double index, I've got to reconstruct where I am in the array based on my block number and my thread number. Okay? And a simple formula says I'm going to stride by the size of the block, in this case 4, times the block index, so 0, 1, 2, 3, and that would give me the start of this block, and then the thread tells me the offset within the block. Okay? Another way to think about these is as MPI ranks, except you have a two-dimensional rank in this case. The rank can tell you, or the block in these indices, loop variables, tell you which the local rank and the more global rank. Okay. Just to confuse you a little bit more, we'll actually use the variables that CUDA provides to you. We'll use, instead of block ID, block index, we'll use the fact that these block indices themselves can be multidimensional. Okay? So this is just mutating code. Okay? So this says loop over the blocks. This says loop over the threads, and then reconstruct the index into the array. And then I've got this magical little if statement. What's the deal with the if statement? My original serial loop didn't have an if statement. Got to make sure I'm in the bounds. Exactly right. Because what happens if your capital N is a prime number? You'd be kind of screwed, right? Because you wouldn't be able to nicely partition it into smaller tasks. And then in a master stroke of computer science versus common sense, the instructions that CUDA requires is just this piece of code in the red block. The for loops go away. Why do they go away? Because we're going to create a block for every iteration of the outer loop, and we're going to create a block of threads for every outer iteration, and we're going to create a thread for every inner iteration. Okay? So we're no longer iterating over an index space. We've just created a one-to-one map between the threads that we're creating and the work we have to do. And then we're relying on these intrinsic variables that are supplied by CUDA. So just to recap, we'll get there. This is what the instruction set for the CUDA kernel, that's the program that's going to execute on the device. That's what we provide to CUDA. Does that make sense? Yes?
Question, what determines the value of block dim?
Fantastic question. We'll fix that in a moment when we go back to the real regular code. And it is another piece of daft CUDA syntax that will let us specify the block dim, the grid dim, and so on. The block, yeah. Okay? So the question is, how do you specify how many threads per block? Well, I'll show you how to do that in a second. Anybody else? Great question.
So this is, I see that this is .x. I believe that it would be .y and .z as well.
Right.
With more higher dimensions. Do we?
I'll get to that. But you're not restricted to a one-dimensional thread array. You can actually have multi-dimensional thread arrays up to 3 dimensions. Okay, in each of the blocks and the grid.
So if there's dim block and around your block dim, is that meant to be that way or is it a typo?
I'll get to the code and you'll see. It's correct. Okay, so let's go back to our masterpiece of code here. I'll maybe make that a little bigger even. Okay, so we now have to face the grim reality of actually designing that the map between the thread space and our task, right? There's a couple of other things that you have to do. In order to tell the compiler that this is actually a kernel, we need to annotate this function. 2 underscores. The CUDA guys loved underscores. Right. Fortunately, nothing else there has to change. Okay? But we do need to nuke that for loop, right? Because the for loop is a serial concept, but we need to back out that n index from a set of threads and a set of blocks of threads, right? So we'll use that same handy formula, which says go this far along in my thread block, and this far along that's how we find out our thread rank in the block and our block rank in the grid. Oh, .c. Oh boy, that would have been awkward. Right, thank you. This just says, assuming, and here's an awkward thing, right, because the context of how many blocks and how many threads per block is divorced from this piece of code. So that requires us to coordinate. When we call this function, we're going to have to specify the block dim and the grid dim. Yes?
So are these blocks like 2 or 3 dimensional grids? Is that why we have an X?
They can be, yes. Yep, absolutely. So that'll be our little code. We nuke that for loop because we're not iterating in any normal sense. We have given over the task of iteration to saying, actually, let's just create a thread per iteration. So we nuke that, but we have to check something. We have to check that this is a legal index. So we have to bounds check. Ta-da! There's your first CUDA kernel, right? Notice, we really do need to make sure we're passing in device arrays here, because this is code that executes on the GPU. So it really needs to be accessing the GPU memory. I've got 15 seconds left. So the last thing we have to do is specify, whoops, how many thread blocks and how many threads per block. I've still not come up with a good variable name for this. So n threads per block. It's very verby, isn't it? Let's say 10. N blocks, or n thread blocks, just to be clear. Now, how many thread blocks do I need if I'm going to have 1 thread per entry? So you might be tempted to do integer division. Oh, sorry, that's wrong. N divided by that, right? N threads per block. But that's awkward. What happens if we have 11? N is 11. You divide by 10, you get 1. So we'd have 10 threads. We'd be short some threads. So this little trick, which will take you a second or two to process, is to round up. All that says is just round up to a large enough integer such that n times n threads per block times n thread blocks exceeds n, or equals or exceeds n. Okay? So just think modular arithmetic. And then I have to tell the kernel how many thread blocks and how many threads per block. So you can see why I always abbreviate those variables, because otherwise it's a bit of a mouthful. And then the last insanity in CUDA is the chevrons. The less than, less than, less than, greater than, greater. It's confusing because it kind of looks like templating, but it isn't. But it's an extension. That's why we're using .cu, because we're using the CUDA extension to C++, and it's not standard C. Okay. Who thinks this will work? Yes, thank you so much. That is why we put those DAs, DBs, DCs, because it's so easy to trip over and pull out pointers from the wrong space. Anybody else? Now do we think it'll work? Yeah?
Is there an implicit barrier at the end of the kernel call?
Oh, fantastic question. Wow, you must be a threading guy. No, there is not an implicit barrier at the end of that kernel call. We have injected a request into the queue to perform that task. Remember, this is a quasi-autonomous compute unit. It maintains its own queue of tasks. We've said, put that on your to-do list. At your convenience, we'll check in with you later. But then we followed it by a CUDA memcopy call. The CUDA memcopy call in this instance is a blocking call. It will block, because it's injecting this CUDA memcopy after the kernel invocation. It's later in the queue. It will wait for that kernel to execute before copying the data. So that's our synchronization right here. Who thinks it'll work? Yes, sorry.
Passing n, or is that fine because it's not a pointer, so you don't need to put it on?
Pass by copy. We're passing a variable by copy, and in fact, we're actually, this is a call to the CUDA API, and the API is going to inject a copy of n to the device, a copy of this pointer to the device, the 3 pointers to the device. Okay? Man, you guys are really alert. Yes?
So, suppose that add vectors call, I have 5 more add vectors. So will that be executed on different portions of the GPU automatically?
No, they will be put in line. One, then the other, then the other. We can create separate CUDA streams, but they would be, it requires some extra API magic. Okay? Okay, should we try it? Because I'm out of time. Yes?
So you say the sequential add vector calls would be executed in order?
In this case, yes, they're injected into the same queue. Okay. Okay, let's compile this guy. NVCC, because we need to use the Nvidia CUDA compiler. Well, bugger. Actually compiled. Can't look. Ta-da! And we have to take a break. I was stumped for a moment by one person who I think is not here. How many people got zeros? Let me use my magical powers of deduction here. Are you on the login node? Are you on the login node? Double check that. And someone over here? So one of the, yes, hello?
I put number 6.
Yes? Okay, are you on the login node? You cannot be on the login node. You've got to be on the compute node. We'll check you later.
So I had the kernel code, I had and equals thread.
Ooh, yes, you sent precisely nothing, because the index, unless, well, maybe you get 1. I've solved your problem. You're in a login node. The login node, but somehow, check your terminal. You'll see. The problem is, many of these systems do not waste a GPU on the login node because you're not supposed to compute on the login node, right? So they don't want to put that temptation in your way. However, it is common practice to compile on the login node. So they've got the CUDA compilers and the SDK and everything installed on the login node, but it's silently failing for you. With very generously pretending there's a GPU, but essentially not executing any instructions. Okay? That's what's going on there. Okay. So what was the category of exercises we heard about yesterday? It was block and random. Okay? Well, let's do a little bit of a hybrid between the two of them. Given the code you now have, everybody has written their own add vectors code. Now think about this example where instead of adding 2 vectors, you're going to take vector A and you're going to write it in reverse order into vector B. So the first entry of A becomes the last entry of B. The second entry of A becomes the penultimate entry of B, and so on. Right? So you're just swapping the order, reversing the order of the entries. Okay, would you like to discuss this, or do you just want to try this? Try, okay? There is no try, but... So why don't we let you guys design your own thread model and get this working, okay? And then we'll come back to it and you can tell me how you did this. Make sense? Okay, so this is your challenge exercise. And buried in this problem is a memory model question. You have to think about that carefully. Okay, so I'll just work through this. I just had a comment that says in Fortran you would just do this, which is very true. Nobody says that this is an ideal solution, right? That's why we're going to hear from Raja and Kokos that they're going to elevate this game to something more sophisticated later on. So if I just copy that main example to call it reverse. Okay, so the task was reverse vector. We no longer need C. B something equals A something, right? And I think the formula was just n minus 1 minus n, right? So I only need to do it once. Kill that last entry. And then we'll just copy B back. And we should be done. Okay, I've got some sloppy extra memory there we don't really need. Okay, so that wasn't particularly complicated, right? We just have to decide how many threads we need. In this case, we are reversing all the entries in the array, so there's one task per entry. There's no potential collision between writing an entry of B and reading an entry from A, so we're okay to do that this way. We have as many threads as things that have to be read and written. So if I make sure I'm on the compute node, and I've only printing out the last, well, that's kind of curious. Oh, because I've got 1 plus n here. Let's just do that. Tidy up a little bit. Get rid of this extraneous stuff. We no longer need the copies here. Oops. Do need to allocate B. Don't need C. Don't need to copy the stuff to B. And we've got the rest of it. So, oops, I'm freeing something that doesn't exist. Better tidy up. Where did C? Oh, it's just a pointer. Okay, try that again. And there we go. So that's, in some sense, a fairly straightforward example, right? We just have n threads. First thread reads that entry and writes to the last entry of B. Second thread reads the second entry and writes to the penultimate entry. Now let's up our game. And let's do an in-place reverse. Okay, so I'm going to call it in-place reverse. .cu. Oh, bugger. Now what I've got to do is, if I play that same trick, I'm going to have a problem, because I want to read from A and write to A. So I'm going to nuke B. And if I have n threads, what's the problem? I have n entries, but can you speak up?
You're writing to memory that another thread can be accessing.
They're going to be fighting, right? You'd have n threads fighting for n entries, but the thread at the beginning and the thread at the end are in competition for those two values. So what should we do? N over 2? Take half the threads, right? So how do we do that? That makes sense, right? We're going to restrict number of threads to half the threads. Yes?
Could you explain why that would help? Because it seems, even if we had half as many threads, if you read from the beginning of the array right at the end, and then the next thread has to read at the end, it's going to read the already reversible value.
We have concurrent threads. So one thread could read a value and write it to the end value, but then that last thread has the wrong value. It'll read the first value and overwrite the value, so you'd have the first value at the beginning and the end, potentially, right? Okay?
I think it should be m plus 1 over 2.
Really? Would you like to substantiate that?
Well, if there's an uneven number of n.
What happens to the middle entry of an array when you reverse it?
Okay, that's true. Right. For this particular one.
But I will give you a lot of credit because I had to think about that fast when he mentioned in place. Yes, absolutely. So the issue is, right, what about an odd number of things and you've got an entry in the middle? You don't need to actually move that, right? Okay, so that's not quite the right thing we need. We're going to say float A1 equals the first one, float A2 equals the last one, AN equals A2. We could have actually done it this way, right? We could just say AN equals that, AN minus 1 minus N is A1. Okay? And the memory model, so there is a question here about memory model, right? So here in this case, this thread has a coherent viewpoint of the entries in this array, right? So these operations will happen in sequence, and you should not get unexpected behavior because only this thread is touching these two entries. Do I need to change anything else in the code? What's that now? Oh, yes. Not your day today. Because we have to copy from A and A, and we get rid of the last thing, and we print out A. Anything else need to change?
So you don't need to take as many threads.
Yeah, I could be lazy and leave it as it is, and all those extra threads would just not do anything because of that if check, right? So really, the number of tasks is n over 2, so I can just do that. Okay? Oh, thank you. Free? Yeah, we should clean up. Yeah, I'm very lazy, apparently. We don't need B anymore. B's gone. A, B. Okay, anything else? Yes?
So I did it without having the intermediate value, and I still managed to get the right reversal. So I wonder if there's like some detection in the compiler to avoid these race conditions or something like that.
Just do it 1,000 times with a large enough. So if, what was your number of threads? 10 per block? Yeah. Do it enough times and you should see some weird behavior. Okay. So MVCC just in place. Ta-da! Right? Hopefully that looks right. Okay. So notice that we had to be more conscious when we were constructing that thread model, right? We had to figure out, okay, there is this possibility you have two threads fighting over the same value. One, you might get into a read-write condition. You might accidentally transpose some numbers or just not touch the data in the right way. So we had to construct that thread partition or loop blocking in a smarter way than if we were just linearly accessing the entries in the arrays. We had to be very precise to make sure we weren't going to get into any read-write race conditions. Because remember, Massively parallel chip, 1,000 floating point units, concurrently processing entries in an array. You run into all sorts of possibilities of race conditions. The simplest thing to do, what is the simplest thing we could have done to avoid any of those race conditions? Sorry?
Some critical region.
Syncing, no, you cannot sync in a kernel, you cannot sync safely between thread blocks. Copy. You try to avoid reading from an array and writing to that same array. It's a very simple rule. It might mean some redundancy in storage. Fortunately, GPUs now have up to 32 gigabytes of memory, so it's becoming less of an issue. But the most natural GPU codes typically avoid read from an array, write to the array, because of the potential for threads competing to write or read, and/or read. Okay? Now, during the break, I had some fantastic questions, the best questions yet, which is, why on earth am I using 100 threads per thread, or 10, even worse, 10 threads per thread block? What's wrong with using 10 threads per thread block?
It's not fully loading.
So you say maximum number of threads per core. What was the other one?
Not fully loading the GPU.
Not fully loading a GPU. This is a pathetically small problem for this GPU. There are less entries in this vector than there are execution units on one of the cores. We're insulting this GPU's intelligence, right? And that's probably why you were able to do that in-place reverse, because you have less threads than we have threads of execution units in the single core. So it's probably all synchronous. Not having a big enough job for the GPU, that's important. But what was really an insult to some of these vector units is we were only using 10 vector units out of 32, right? That's the ultimate insult to a vector unit, is to populate it. So what should we have used as our threads per thread block? Maximum? Yep, that's one way of doing it. Absolutely. That would be a good way to do it. This is an early GPU, so I can't remember if the maximum number of threads was 256 or 512 or 1024. It was a moving target for a while. It's settled at 1024. Just means they have a 10-bit thread index for each thread. Let's say we could have done that. That's a fairly safe number. That was supported by early CUDA through late CUDA. I could go to 1024, but that may be, I can't remember when CUDA switched to using 1024 as the maximum number of threads per thread block. For this task, it doesn't matter. Because this task is a block access, essentially a linear access of an array, no complicated things happening inside this thread block, multiples of 32 would be fine. So what happens in the core is that if you say I want 64 threads, they get chunked into groups of 32. And they'll push 32 through one of the SIMD units, one SIMD vector units, and they'll push the second group of 32 threads through a SIMD vector unit. Okay? And lo and behold, then it'll run. The question that came up, which was quite a nuanced question, is what happens if I need more threads than there are floating point units on the whole device? Let's say this thing has 2,000 floating point units, but I need 10,000 threads because there are 10,000 entries in the vector, on the vectors. What do you think happens?
Essentially, if you create more blocks, they get scheduled serially.
Perfect. There is a scheduler on this GPU which takes these thread block tasks and it will communicate with the cores, and the cores basically have flags that say, I'm ready to take on more tasks. One subtlety is that this task, this block, thread block, gets all the registers and variables needed associated with executing that task for those threads has to be concurrently resident on the core. So as soon as it gets loaded up to the core, it's on there. All the threads, all the registers, all variables they need are on that core until they finish. Okay? So there's some subtlety there. The GPU favors thread block tasks and thread tasks which are fairly lightweight and don't take thousands of registers. Although they've got thousands of registers on this, variables in each core, you want as many threads as possible so that the scheduler inside the core can keep switching in and out between threads so that threads that can be active are active as much as possible to do.
Clarification, the scheduling happens in blocks, right?
Yeah.
Okay.
There are two, remember this is two-level parallelism. There's the scheduler at the level of the device. That is basically doing traffic control for blocks. It's sending blocks out, block distribution to the cores. There's a second scheduler or multiple schedulers on each core which slices and dices those blocks into groups of 32 and send them through the SIMD units. Okay. So do you think that has helped you understand the architecture? It's a multi-core. Each core is a multi-SIMD unit, right? The programming model is kind of heinous, I will say that, right? It has separated two very important things that should not be separated. The work inside for loops, the parallel for loops, and the specification for the bounds of the parallel for loops. Right? Remember, the for loops disappear, the bounds for the for loops are put into the chevrons at the launch of the kernel. That makes it a little bit tricky to coordinate in code because now you've got two critical pieces that are separated into different function parts of the code, right? The thing that happens inside the parallel for loop and the specification of the bounds for the parallel for loop. They are divorced. That is one of the biggest mistakes that Nvidia made in the specification of CUDA. By the way, I love the offloading compute model that Nvidia uses for CUDA. I really like the way they've constrained you to the parallelism unit is parallel for loops. That's great. That focuses you. There aren't fancy forking tasks, whatever, this stuff that OpenMP is trying to get you to do, right? Keeps you very focused. You can basically have parallel for loops, some atomic operations we haven't talked about, and some synchronization and shared memory. That's all fine detail you get as you get further into CUDA. But there's only one real parallel concept, which is parallel for loops which are obtained through loop blocking. Okay? That focuses you a lot. You don't have this paralysis of choice with OpenMP. In OpenMP, you got that flavor that there are 10 different ways to do something in OpenMP, right? You can do parallel regions, you can do tasks, whatever, right? Here, you're kind of stuck with vanilla parallel for loops. So that's great. But the syntax and the way that you construct these programs does leave something to be desired. Okay, so let me skip a little bit. You've done that part. To answer the question about multidimensional thread blocks, yes. You can have currently, I believe, 3-dimensional thread blocks and 3-dimensional grid of thread blocks. So you could imagine a volume of threads, and you can divide it into a bunch of Rubik's cubes, and each of the little color blocks in Rubik's cubes are thread, but you can have a whole stack of Rubik's cubes, and that could be a 3-dimensional stack of 3-dimensional cubes of threads. Well, not cuboids of threads. Okay. So then I have some worked examples for an elliptic solver, Poisson solver. Okay. Now, keep in mind that the only available parallel model you have is parallel for loops. Then you might ask yourself, how do you do a reduction? These are the big moving parts in parallel codes, right? We've done embarrassingly parallel tasks. Now the question is, how do you coordinate reduction? The sum of entries in an array, for instance. Okay? So the reduction looks like sum all the entries in an array. The block reduction, which if we start thinking about this two-level parallelism, you always have to subdivide the task into chunks or blocks, and then subdivide the blocks into subtasks. Well, again, you turn a single sum, which is basically a loop over variables, into a double sum. Okay? Same type of block reduction. And then in pseudocode, if this is our vector, we're going to do a binary tree reduction on the variables in the array. Have you seen binary trees before? Okay. So the trick here is we're going to have to coordinate between the threads in the thread block. So each thread block is going to load up a certain number of values from memory, and then they have to be able to coordinate the sum of those values. And one way we can coordinate that is to put those values into shared memory. Remember, each core has its own shared memory space, which is visible and accessible to all threads in a thread block. So they use a scratch pad, coherent scratch pad, and in this case, I've got 8 threads. They're going to load 8 values, and then I'm going to turn off 4 of the threads with an if statement, and then let the first 4 do the first part of the addition. So they'll each add 2 values and write 1 value to shared memory. And then we'll keep repeating that, dividing the number of active threads by 2 until we've got 1 thread left with the answer. And in this case, we can just let that thread write out that value. So we're not collapsing the whole array down to 1 value. We're collapsing chunks of the array down to 1 value per chunk. So if we take that approach, what do we do next? So let's say you had 100 threads or 128 threads in each thread block, and you had a vector of length 1280. Then you'll have 10 thread blocks. You'll start with 1280 values. You'll reduce it by a factor of 128 down to 10 values, and you've got a choice. You can either call this partial reduction again to reduce it down to 1, or you can just copy the data to the host and let the host do the final reduction and copy the value back. Okay? So in proper code, it's a little small, but we're using now a scratch pad which we can annotate by a shared array. I always forget I have this thing. We have a shared array, and we'll just create what looks like a stack array, but it's just a shared stack array. And we'll just do our standard thing, which is create a thread map from the thread index space to an index in the array. I'm going to initialize the shared to 0. I'm going to load up, in this case I'm taking the square of the values of difference between 2 arrays, doesn't really matter. Put it into shared, and then start with, let's say, 128 threads are alive. I'm going to synchronize to make sure all these accesses to shared are completed. I'm going to kill half the threads, and then I'm going to say for the remaining threads that are alive, do part of the reduction, and then I'm going to keep looping until we're down to 1 thread, and that last thread can write the value out. Okay? So that's just there. The only reason I bring this up is, 1, because reductions are so important in parallel tasks that I've included it for completeness, but really it's there because it introduces 2 new concepts: the shared memory array and the sync threads. Now, it's important to remember the shared is only shared between threads in a thread block. And if you have threads that write to the shared, you have to make sure they've all completed their write before you start accessing that data in that shared array, so you must call this synchronization. It's basically a barrier. There are refinements to this process, but I'll leave that to you, right? So We don't have time for this, but there's an analog of the Mandelbrot area example that you could do, but that basically involves reduction. So you would adapt that reduction code to do the summing of the Mandelbrot value, ones or zeros, depending on whether a point is in the Mandelbrot set or not. Okay, I'm going to skip the performance stuff. It's just there for completeness. You can refer to it. And I'm just going to address portability in the remaining time. I've focused on CUDA and Nvidia GPUs, but that's a single vendor with a proprietary programming model. I do that, I introduce CUDA first because it's the easiest way to get you up and running and to describe the concepts you need in order to do some basic GPU programming. If we'd started with OpenCL, we'd still be here a couple of hours later because it's an API which is much more complicated. I think you probably got that flavor in the FPGA lecture. You saw that because OpenCL is so flexible, you have to choose the OpenCL platform, the device, and then you have to build the kernel on the fly because there's a combinatorial explosion of possible platforms and devices and so on. So there's a very complicated model. But having said that, we really don't want to bake in a single point of failure for our codes. We invest, I think I calculated once that an academic PDE solver costs about $1 million. Very basic one. You just take the number of postdocs and grad students that are involved. They're expensive. And you just multiply by the number of years it takes them to do something. And you basically just do something fairly rudimentary. It costs $1 million to write one of these codes. And if we just wrote in CUDA, which we did our original codes, then you suddenly depend on a single company. And the half-life for a tech company is not that long, right? How many people have SGI computers? They were all the rage. How many people have Sun computers? They were all the rage back then. They're still on life support in some ways or other, but tech companies come and go. This is a very sad story. This is Blinky. Blinky was a MacBook Pro, and it was the last generation Nvidia Apple computer that had a discrete Nvidia GPU. Subsequent Apple MacBook Pros have AMD GPUs. So right there, now you cannot run your CUDA code natively on an NVIDIA GPU in your Apple laptop. Blinky died because Apple. And I'm left with a problem. Well, I could run OpenMP on this thing. But what did Apple do with OpenMP? They introduced Clang, the C language compiler, which doesn't have, or didn't have, native OpenMP support. Right? So then you have to start bolting in the GNU compilers. So you end up in sort of chasing the latest available compute model. So we don't want to get into that business. Now there are several ways, and this is a little out of date because I haven't updated this, but basically you could use OpenMP to program Intel CPUs. It can even kind of program GPUs now. Or you could use OpenACC to kind of program GPUs. Or you could use CUDA. Or you can use OpenCL. Oh, well, OpenCL seems promising, right? You can pretty much program anything that you can connect to a computer, right? Even up to FPGAs. What's the problem? It's low level, so we'll see Raja and Kokos in a few minutes. What else is a problem? Support. Someone say support? Support, yeah. Very good. You'll go far. So the problem there is that we're relying on all these manufacturers to provide OpenCL implementations. Now, OpenCL was largely put, and this is my interpretation, it was a standard put together by the Kernels organization And some of this effort was driven by Apple as the 400-pound gorilla that could actually use its market position to force the vendors into producing OpenCL implementations. So somehow, magically, Apple managed to get AMD and Nvidia, who are deadly rivals, to actually produce a common standard. Ever since then, Nvidia has been trying to deprecate OpenCL support. But you know who beat them to it? Who actually dropped OpenCL first? No, Intel has OpenCL support. Apple. So Apple brings them together in a very awkward marriage, a shotgun marriage, and now Apple's walked away. So I have my doubts about the long-term viability of OpenCL, except now Intel is interested because they bought the FPGA company Altera, right? And in order to program, for a mere mortal to program FPGAs, you use OpenCL. So there's this bizarre sort of game of chairs, musical chairs, that happens with this standard. Now, skip a few things. So as I've sort of speculated, CUDA comes out in 2007, 2008. It catches on pretty quickly because people are getting great performance. Much better than naive CUDA codes could be much better than naive Intel codes, right? So Apple pays attention and sort of forces the OpenCL working group, and within, and you can see between May and October, so that's what, 5-6 months, they produce a standard. How do you produce a standard in 5 to 6 months? In a committee with all these different stakeholders. You don't. You take an existing solution and you change the syntax. And we have OpenCL. OpenCL is very closely, I'm being generous here, closely related to CUDA. So the terminology, kernels, host programs, threads, thread blocks, grid, have OpenCL variants. This nasty thread index thing, we now have API calls. Okay? So if you're in a kernel, an OpenCL kernel, you want to know your thread index, you call the get local ID. You want to find out how many, what the size of the grid is, you can find out through API calls. So everything has an analog. The function annotation, global becomes kernel. That kind of makes more sense. Device just becomes, this is just a function called from inside a kernel, becomes a function and so on. So there's a one-to-one map. There's a one-to-one map between the language, and there's a one-to-one map between the memory model. Unfortunately, OpenCL comes with some extra bonus things you have to do. You have to choose which manufacturer's OpenCL to use, which device you want to use from the available devices, and then because this is something you're bootstrapping from the get-go, you have to create a manager, you have to create a queue. Apple really is a pain in the ass that they couldn't even come to the table on deciding what to call a header file. So you can look at what you have to do extra in OpenCL. You have to get a list of platforms, choose the device, create a manager for the device, create a queue for the device, create a because this could be any number of different things. You've got to create a program resource, build the program, check to see if there's any errors when you build the program, and then create the kernel, which is an executable version of the program. To execute it, you need to create a buffer like you would use CUDA malloc, but you need to create a CL create buffer. You need to set the arguments because it's not a callable, an OpenCL kernel is not a callable function. So you have to set the arguments one by one, and then you have to enqueue it. Okay, so if you compared the code, OpenCL is rather more verbose. The only thing that's simpler is that the kernel syntax is a little bit cleaner. Okay. I'm not expecting you to absorb that, right? So OpenCL, actually, to be honest, has a bad reputation. CUDA has more tools, better ecosystem, more extensive documentation, reduced complexity because it's single vendor. OpenCL has competing vendor priorities. and the vendors offer different levels of support. And rumors constantly circulate about end of life, right? So there was, in fact, an announcement from Nvidia personnel, not Nvidia, that they would be end-of-lifing OpenCL support. On the other hand, it does runtime compilations, so you can do more optimization. It's library-based, so no special compilers, and it's vendor-independent. So this is just the example I've worked through, so you can see how similar they are. But the API sucks, and we don't know how long it's going to live. So as good software developers, we say, I'm going to abstract. So the abstraction says I'm going to step away from littering my code with OpenCL API calls or CUDA API calls. I'm going to put it behind a window or behind a curtain, right? So we'll Wizard of Oz this thing, put the threading model behind a window, and not worry about the code dying as soon as one of the OpenCL dies or CUDA dies or whatever. So there are a number of different approaches to portability. Some of them are popular. They go from Nvidia CUDA code by conversion to OpenCL or AMD's HIP approach, which is sort of a version of CUDA, or some similar level, it's basically binary conversion. And then you can target whatever platform you want. This is all a bit specific to OpenACC. And in terms of maturity, I'd say CUDA is pretty mature. HIP used to be down here, but we actually now are finite element codes. They run in HIP or CUDA or OpenCL. So these are all very mature and usable in a sense. But we're still left with this problem of, if you're going to, the classic problem you've got to solve now as a developer is MPI plus X, what is X? And I say it's too early to decide what X should be. So we hide X, whatever that be, OpenCL, OpenMP, CUDA, or HIP, behind some curtains, and we choose at runtime which of these we want to use. And here's where I've got 4 minutes to pitch my product. Ocker. It's a product out of a PhD thesis at Rice University by David Medina, who's my PhD student. It's got some nice web pages. Some of it's complete. It's addressing this issue. This makes more sense if you're English. Who's had Marmite? Okay. Is Marmite like an insult to your taste buds? Yeah. It's a yeast extract that's a kind of brown, goopy stuff, right? And if you grew up eating it, you love it. If you didn't have it as a child, it is an abomination. Okay, and that's how GPUs are, right? Because you're forced to adopt something you have no taste for, because you have no experience with it, right? So Ocker's our attempt to hide the GPU Marmite taste behind an abstract interface. So you can program. We have a front API in C++, C, or some Python stubs. You interact with our API, and you don't have to touch CUDA, OpenCL, OpenMP, or Threads directly, and we'll automatically manage everything behind the scenes. And now the fee went away, but it does not matter because we did not invest very much in fee. We didn't recode for fee. It was hidden behind a low-level thing we'd abstracted away. And we've added AMD HIP support. So now we basically have vendor-approved programs or codes that will run natively in CUDA, natively in AMD HIP, or in OpenCL, OpenMP for x86. So it's all done automatically behind the scenes. What does it not do? It does not auto-parallelize. You still have to think in terms of kernels, in terms of thread models, but it uses the same syntax and the same API in order to interact with all these different back-end models. It does not decide how data should be laid out. We'll leave that to Kokos and Raja guys to sort that out. You can use it with MPI, but you have to write the MPI code. We considered doing a mocker version with MPI built in, but it quickly devolves into a parallel global array code we didn't want to write. And we do use vendor compilers. You can try it out. It's very easy. So where does it live in the hierarchy? At the top, so if you go from bottom to top, you've got the different types of portability. You have binary translations in Ocelot, all the way up to CUDA core, which is source-to-source translation. It's another VT product. Ocker, which does source-to-source, has an API, also has its own kernel language, and it directs to CUDA, OpenCL threads, OpenMP, and HIP. Raja, similar type of coverage, but it's a library and it's a higher level library, but it uses C++ lambdas. And then you go up to Cocos, much more sophisticated, a bit higher level, and you can see this is, I think, if you're a domain specialist, this is where you want to be, at this abstracted level. You really don't want to be in the business of writing your own CUDA code. I introduce CUDA so you get the concepts. But to be productive, you really should be sitting at this abstraction level or higher, just to be productive. It has its own kernel language, and because I think in terms of for loops, we put the for loops back into our parallel kernels. And we do the detective work to figure out what the bounds are we should feed to CUDA or OpenCL so that the stuff in those fancy brackets, we populate that for you behind the scenes. Right? So we have our own code parsers that do that kind of work. Right. They're going to tell me to wrap up in a minute. We have shared memory and thread private variables that can be used. So this is an example of a piece of code that does that add vectors example. And this, if I can just, whoops, I'll get there eventually. Nice thing is that at runtime, we can decide whether we want to run it in OpenCL, HIP, CUDA, or any other OpenMP model. And then everything else is handled behind the scenes. Okay? So that way, I'm not limited to CUDA or Nvidia or AMD or Intel or whatever the flavor of the month is. If there's a new architecture from Samsung GPU or whatever, we will put the API calls behind our interface and work through Ocker, and our high-level codes, which are not insubstantial codes, don't have to change. So there are different flavors, different APIs. We had a MATLAB interface, but let's say we just nuked that, right? Behind the scenes, we do some very clever stuff with caching so that if you run this on a big system, you don't have to recompile for every MPI process. We actually use a cache system so that you compile once and get reused. So the last thing I'll have in my -3 minutes is this hands-on number 3. If you work through this process, and if you want to send me your movies, has anybody made a movie? Cool. If you send me your movie, I will create a drive, and I'll send Marta a link to the drive, and then we'll send you a link to a survey, and you can vote on your favorites. So we'll collect these movies until, is tomorrow going to work? You should be able to use this system. And the instructions for writing and building the movie, and the more creative you are, you can change the palette, you can change the image, you can even change the physics if you're feeling brave. But the instructions are there. And as I said, based on the feedback from the poll, we'll give out prizes in a couple of days. Okay? So there's some stuff, but let me just finish with everything we've done today. You can do on Cooley or a GPU-equipped machine, but you can also go to one of the cloud providers. So we regularly use the Amazon AWS EC2 GPU instances. We use the Paperspace instance. We also use the GPU Eater instances because they do all the maintenance of these GPUs for us. When we get to big runs, we come to data centers like, or compute centers like ALCF. Okay, thank you very much.